Okay, yes, I'm live. All right. That didn't work, so I'm not happy about it. Okay. All right, so how's computation like a sandwich? Anybody have any ideas? Well, it says so right on the slide. It doesn't really say on the slide why it's like a sandwich, but we're getting to that. So here's my analogy. You're running a sandwich shop, and somebody orders a couple of sandwiches. So what do? You can have one employee make one sandwich, then make the other sandwich. You can have one employee make both sandwiches. You can have two employees, each making a sandwich. What's the correct answer? So I'm just going to take a quick poll. How many people think it's number one? Nobody. Okay. Number two employees. A bunch. Number three, one employee, two sandwiches. And a bunch of you have abstained, probably because the actually correct answer is, well, it depends. And but this is, surprisingly a pretty good analogy, at least I think so, for the different kinds of parallel computation that you can do in a computer. So today, so how many here were at Joe Falco's talk on Monday about boost.simd? Nobody. Oh, a couple of people, okay. And what about Nicholas, I'm sorry, I don't know how to pronounce Nicholas's last name, Guillemot's talk yesterday? Just a couple. Well, all right. There's a little bit of overlap in this talk, but one of the big differences is that Joel was talking about slicing salamis in parallel, and I'm talking about making sandwiches. So really different subjects. Both food related. You have to have food in your talk. So my name is Pablo Halpern. I'm an Intel employee, engineer. I've given talks at CppCon in the past about parallelism and multi-core parallelism in the past. Today I'm going to be talking about vector parallelism, which is actually the most common parallelism in your computer and the one that is probably least well understood. So my goal is for you to understand why it's important and how to give you a head start on programming for SIMD in your C++ code. This is a kind of a broad talk. It's not real deep dive, but I hopefully will give you enough to get started. I want you to hold your questions to the end if you can, unless something is really unclear or you really need to interject, because I timed this talk and it's really just right on time to leave about 5 to 10 minutes for questions. Okay, the last thing that you need to know is why is sandwich making like parallel programming, vector programming. So what is vector programming? Well, we start with this notion that we have a computation, and I'm just kind of labeled the steps, A, B, C, D, and you have a bunch of data that you need to process using these 4 steps, which I labeled 0, 1, 2, and 3. And we do the steps in parallel using a single instruction executing, in this case, in this diagram, 4 pieces of data at once. So single instruction, multiple data, SIMD. Throughout this talk, I'm going to be using SIMD and vector parallelism more or less as equivalent terms. They're not exactly equivalent. In addition to the short vector SIMD, which we find in most modern CPUs, there's also long vector machines like the old CDC supercomputers and connection machine supercomputers. They use a thing called long vector. And then there's also pipelining architectures, both in software and hardware. And they all use a very common programming model. So most of what we talk about here would apply to those. But I'm really mostly talking about the SIMD architectures that are in the CPUs today. Suppose we have a computation that's, we're trying to speed up computations, and it doesn't really makes a lot of sense to speed up a computation on 4 data items. But if you have 1 million data items or 100 million data items, that's when you really want to see some speed up. And of course, our SIMD machines, even if they can do more than one thing at a time, they don't do 1 billion things at a time. So we have to chunk them. And the chunking is very straightforward. In this case, assuming our vector width is 4, that is how many operations we can do at once with a single instruction, or how many pieces of data, we can operate on with a single instruction. we do 4 at a time, all the way through the body of our loop, our hypothetical loop here, and then we move on to the next 4. Pretty straightforward. If somebody was giving you the SIMD machine and said, here, we can do these 4 at a time, this is probably what you'd come up with as how to get the entire loop done, right? Now, what if you don't have a multiple of 4 items, right? Well, we're going to get to that. You're going to have to be patient because that's kind of close to the end of the talk. But there's a thing called a remainder loop that takes care of the last few items that don't fit, that are less than a vector's width. What's happening in the hardware is that we have our CPU and we have our instruction fetch and decode, which is stuff that you probably have heard of before, that even has been around in CPUs forever. A bunch of scalar registers, memory subsystem. But then the thing that is new, and I say new in quotes because it's been around for quite a long time, like 40 years, are these SIMD registers, which are these wide registers that hold more than one data item at a time, and multiple floating point units and multiple arithmetic and logic units to do the arithmetic on more than one data item at a time. This is highly simplified, but is the basics of what we care about. If we zoom in on the SIMD register, it actually behaves like a whole bunch of registers at once overlaid on top of each other. So an SSE4 register, that is the instruction set of previous generations of Intel chips, and which is still supported in all of the new chips, has 128-bit SIMD registers, and they hold 2 doubles or 2 longs or 4 floats or 4 ints or 8 shorts or 16 chars. And of course, all the integer types can be signed or unsigned, it doesn't care. So depending on what data type you're computing on, you can have more parallelism with the shorter data types. And often there's a lot of computations for which floats have plenty of precision. And so a lot of times people modify their code to use floats instead of doubles to really take advantage of getting that 4x speed up instead of 2x speed up using SIMD. In the AVX, which is the new generation, the newer generation, and still not the newest, the registers are 256 bits wide. In the AVX 512, they're 512 bits wide, so you just quadruple the numbers that we just looked at. It's really convenient to think of a SIMD computation as being 4, in this case. I'm going to keep using 4 throughout this talk because it was made for really easy diagrams. If you're doing 4 computations at once, it's fairly convenient to think of them as 4 separate streams of computation on 4 separate data items. And we call those streams, we call those lanes. But it's really just a model. Because under the covers, it's really important to remember that lanes don't really exist. What you have is SIMD registers, and you have these things happening in lockstep. And the most important thing that's different between the lane view and the real physical view is that this lane view can give you the misimpression that you can have independent computations going on, when in fact, they're not independent at all. They have to be in lockstep. So because they have to be in lockstep, that causes a problem called control flow divergence, or control flow divergence is not necessarily a problem, but it is for SIMD. What happens is if you have an if statement, and some of the lanes want to follow down one path, and some of the lanes want to follow down the other path. If they're in lockstep, how does that work? Well, ideally, we have a masked execution, and I say ideally because there's ways in which you can get around it for older architectures, where we have a mask of bits that say which lanes are active for this instruction and which lanes are not active. A 1 bit or a true value is for the ones that are active, a false value for the ones that are not active. And so we start our computation, we'll assume that the mask is set to all 1s. So the A computation, which as you can see is not inside the if here, takes place on all 4 lanes. then inside the if we compute I modulo 2, which for the odd numbers is going to produce a true value, and for the even numbers a false value. And that's going to generate a mask of true false values, which is this 0, 1, 0, 1 here. So for the next instruction, the mask is going to be 0, 1, 0, 1. And that means that for the then part of the if statement, the B instruction, the first and third lanes are masked out, as we say. They do not perform the computation. And in the else, we invert the mask. So when the mask is inverted now, the opposite lanes are active, and the C part takes over. Okay, and the C instruction executes only on the first and third, and not on the second and fourth lanes. And then we set the mask to all true again, and execute D in all the lanes. Now, I said ideally, because there are some architectures, in fact, many architectures in the whole SSE line that didn't have masked instructions for all of its instructions. Instead, what you do is you do the computations on all of the lanes at once, but you store the results of the then part and the else part in separate registers. And then at the end, there's a blend instruction that says, using this mask, take the appropriate ones from this temporary register and that temporary register, and we combine them together into a single register, and that's your end result. Okay, so that's the way we did it before AVX. Okay, and on the Intel machines. I'm not really sure about the Neon and Altivec and others, but I assume that the newest iterations of those probably do masked execution. So let's go back to our sandwich analogy. We want to make a sandwich efficiently with one person with two hands. Now, although we have two hands, most of us are not very good at doing two different things with our hands, two completely independent tasks. So I'm going to assume that we can't, get arugula from over here and lettuce at the same time from over there, because if I tried to do it, I would mess it up and have to do it 3 times, and it would take 5 times as long. So we have one person. Now let's make 2 identical sandwiches, right? And we're making a BLT, a bacon, lettuce, and tomato sandwich. So we spread mayo on both slices of bread, and we add tomato to both of them, and we add bacon to both of them, and we add lettuce to both of them, and then we close them both, and we're done. 5 steps, and we've made 2 sandwiches. Pretty good. If you're making only one sandwich, it would take about as long, right? Because you still have to do the same 5 steps. Okay, but now we have some control flow divergence. We're making 2 sandwiches, but they're not exactly identical. One of them doesn't want mayonnaise. The other one wants arugula instead of lettuce. So now we have a choice. Do we still make both at the same time? And the answer is, yeah, I think that's the best way to do it. But we have to make a little changes in our procedure. Again, you have to remember, the 2 hands can't be completely independent. So we're going to mask out the steps that should be done for one sandwich and not the other by saying, okay, we're going to spread the mayo on the bread, but instead of doing it for both sandwiches, we're going to do it for just the right one. And then we're going to add tomato to both, and then the bacon to both, and then lettuce to the left one, and then arugula to the right one, and then we're going to close both sandwiches. Anybody notice anything about the number of steps? We used to have 5 steps. Now we have 6. So the procedure has gotten a little bit longer because we've added this if-else that says we've added arugula into the mix. But the interesting thing is, if you were to make the sandwiches one at a time, it adds up to 9 steps. You can do the math yourself, but it's 4 steps for one sandwich and 5 steps for the other. And so it's 9 steps. So you make one sandwich at a time, 9 steps. Here, we're doing it in 6 steps. So we still have a 1.5x speed up over making the 2 sandwiches completely one after the other. But before we had the control flow divergence, we had a 2x speed up. So this is why the control flow divergence is the sandwich maker's nightmare and is not too fun for SIMD either. Okay, an important thing to keep in mind. So control flow divergence cuts down on the amount of parallelism you can get from SIMD. So let's compare SIMD more directly with other forms of parallelism. In the multicore world, computations on multiple iterations of, say, of a parallel loop are completely unordered. So they start at different times, and they proceed independently at their own rate. Something like this. Okay, we've got 10 iterations, and notice that where I froze the action, iteration number 5 is ahead of iteration number 0, and some of the iterations haven't even started yet, probably because there aren't that many CPUs to start them all concurrently. So what's going to probably happen is iteration 0 will complete, and then the same CPU is going to go ahead and do iteration number 1. That's multicore. And I'm going to use multicore and parallel more or less as synonymous terms, even though parallel could also mean vector parallel or other kinds of parallel. But if I just say parallel, I'm referring to multicore. Okay, now let's compare this to SIMD. Let's assume starting with 2 lanes, and the iterations happen in lockstep, the first 2 iterations, and then the next 2 iterations in lockstep, and then the next 2 iterations in lockstep, 2 at a time. Notice that there's a left to right progression, kind of like serial, and that this is more predictable. In fact, it's very predictable compared to multicore. Let's look at 4 lanes. Same idea, but now it's happening faster because we're doing 4 lanes at a time. So we've done 4 iterations all at once, and then the next 4 iterations get started. If you look at the shape of this, you see that it kind of forms a pattern which we call a wavefront vector computation pattern, where the computation proceeds from upper left to lower right, that is from the first iteration towards the last iteration, and from the first instruction towards the last instruction, along this rough diagonal. Now it's a jagged diagonal, in reality, but if you make the extend it to infinity, you'll get something that looks more like a diagonal line, and that's our wavefront. The computation goes along the wavefront. So the wider your vector, the closer the horizontal, the closer it looks to up straight from up top to bottom, and the narrower your vector, so the degenerate case is scalar execution, will go almost left to right. But of course, it's still scanning top to bottom and then left to right, like that. So interesting things to note about that. One is that scalar and vector are very compatible because scalar, you can take any part of the vector computation, and if your hardware can't handle it, can't do it as a vector computation, the compiler can just serialize, or the programmer can choose to serialize that part of the computation, and it falls within the wavefront that the vector is expecting. It'd say, let's do these 4 things at a time, these 4 things at a time, then these 2 things one at a time, one at a time, one at a time, one at a time, and then we go back to vector, next 4, and it's still following that wavefront. Why is this important? Well, there's a very important dependencies that a lot of loops have, certain kinds of loop-carried dependencies where you're looking ahead or you're looking behind at things that should already have been computed or that you are sure have not yet been computed. When I say not yet can be computed, memory locations that you must be sure have not yet been modified. So in this case, we have our hypothetical SIMD loop, and we are looking ahead at the element from logically the next iteration, right? If you think about my iteration owns array element a sub I, this current iteration owns array element a sub I, then array element a sub I plus 1 is logically owned by the next iteration. So what is the progress relationship between the two? Well, the wavefront ordering says they may be, these steps may be occurring simultaneously, but the next iteration will never be ahead of the current iteration. And this is really important. And I'll show you this in the diagram later on when we get to the actual programming of this stuff. So when we read x from this function call on a sub I plus 1, we can rely on the fact that a sub I plus 1 has not yet been modified. Why? Because the step to modify a sub I plus 1 in the next iteration is later in the sequence and cannot have happened yet because the wavefront says it'll never get ahead of me. Okay, so this is legal. This is legal in vector code, and very fast. The vector code just does not care, as long as you've met the requirements. You can't do this with parallel, or you could, but it would be so expensive to do the synchronization and say, wait, I can't look at this yet because, you know, this guy, I can't modify this value yet because my previous iteration hasn't read it yet. So you'd need all sorts of synchronization. That's sometimes useful, but most of the time where people have tried this, they take long vectors first on one CPU, and then they try and gang up multiple CPUs to get even longer vector quality. And there, that do-across computation might actually be profitable. So I think I've said everything I need to say about this slide. So let's look at what we've gained here. So there's less active silicon. Why? We don't have an instruction decoder for every lane. We only have one. We don't have a memory subsystem for every lane. We only have one. So there's less silicon in general and less silicon that is active at any given time to do a vector computation versus doing the same computation on multiple cores where you've got the instruction decoders working concurrently on all of them and so on. So that saves a lot of energy, quite a bit of energy. Especially the wider the vector is, the more energy you're saving. There's no scheduling. This is not an operating system operation. This is just part of the instruction set. There's no, let's take this work and divvy it up. The divvying up is very straightforward, next iteration, next iteration, next iteration. There's no overhead for synchronizing at the end. When the SIMD operations get to the end of the loop, you're done. You've done all of the work. You don't have to send signals back and forth saying, okay, we're all done now, you can continue. And there's almost no overhead for communicating across lanes. So that shuffle operation I mentioned early on where you can rearrange the order of elements in the SIMD register is quite fast. Much faster than if you had concurrent threads that said, you take this value and I'll take that value. And very important, and one of the things I really want to hammer home in this talk, it can do this wavefront computation efficiently. But there are limitations. We mentioned control flow divergence. That's a big one. If you have a lot of control flow divergence, SIMD is not going to be profitable. There's limited synchronization. You can't just take threaded code and plop it into a SIMD registers. If there's mutexes or something like that, you'll deadlock. Why do mutexes deadlock? Well, when you get to say a mutex, remember there's n things happening in lockstep. And say the first one grabs the mutex. And now the second one wants to grab the same mutex. So now you've deadlocked. The second one can't proceed. And the first one can never release that mutex because it's waiting for all of the other lanes to complete. So no mutexes across lanes in SIMD code. I was going to say something, but I'll just confuse everybody, including myself, if I get any farther. Just think no mutexes. All right, blocking operations like I/O, kind of a similar problem to mutexes. They have to be serialized. We don't really have like file I/O happening using SIMD units. But it can be done with multicore if you're careful. And then the last thing is that the microarchitecture determines how much parallelism you're going to get. You can't just say, well, we'll just design the motherboard with more sockets. That won't add SIMD registers. It'll add cores, but it won't add SIMD registers. Now, if you don't require that wavefront dependencies, and there's a lot of computations that don't need them. There's a lot that do, but there's a lot that don't. Then you can combine SIMD with multicore and get the benefits of both. So in that case, it does scale, but within within the SIMD world alone, you can't scale it just by adding more hardware. You have to have a new generation of chip. All right. I'm not an expert in GPUs, so this is the only slide where I actually mentioned them, but they definitely need to be mentioned because I'm comparing different kinds of parallelism. GPUs are kind of in between SIMD and CPUs. The GPUs that are common today have a lot of very small, they're like very small cores, and there's like thousands of them. And they do some things in lockstep, and there's some parts of, there's chunks that operate in lockstep, and then the chunks themselves do not operate in lockstep with each other. So they're not really designed to do these wavefront computations, but they have some of the benefits of SIMD. They do save energy for the certain number, per gigaflop. They tend to be more efficient than a core is. You can get this sort of massive parallelism, but there's all sorts of trade-offs, right? They tend to go through a device interface. So for really small computations, you don't want to use a GPU, but for very small computations, you can start getting benefits out of SIMD. Okay, so I said that we were going to visit the sandwich shop one more time. Here it is. So now let's look at the different kinds of parallelism and see how it related to that very first question I mentioned. Now, nobody said make them two sandwiches one at a time, even though sometimes that really is the right answer. Like when you don't have a second employee, you only have one, right? Okay.
Two of everything mean two hands total.
Two hands what?
Total.
No. Okay. So two employees. So the multi-core approach to sandwich making: two employees, two hands, right? Two hands, but they have to do the same thing. So if you're making two separate sandwiches, you're not getting really that much benefit. I mean, we're stretching the analogy a bit, right? So two employees, they each have their own brain. Okay, think of the brain as like the instruction decoder in the CPU. So you've got two of those. You've got two things. It's expensive. You got to pay. Now you're filling one order for two sandwiches. Now you're paying two employees to do that one order. It requires coordination. You do this sandwich, you do this other sandwich. You can't just have them willy-nilly decide to make a sandwich and discover that they both made the same sandwich when they're supposed to be making different sandwiches. And it requires coordination at the end when they're done, saying, okay, I'm done. Okay, I'm done. Let's put the sandwiches in the same bag and give it to the customer. Okay, but with all that overhead, it's still the best approach. If what you want is the fastest fulfillment of the order, it's still the best approach when they're making radically different sandwiches, right? If one is on rye bread and the other is on whole wheat, and one is a bacon, lettuce, and tomato sandwich and the other is a turkey sandwich, you'll get no benefit from having one employee trying to make two sandwiches simultaneously because they won't be simultaneous at all. They'll be one after the other. In which case, two employees, each making one, will get the job done faster. What about SIMD? Okay, we've already kind of gone through this, right? Now we have one employee, one brain, one wage, right? It's less expensive because there's only one person. There's no context switching or coordination. That's all really good. But if the sandwiches are not nearly identical, you don't really gain anything. You slow down the process because they effectively end up being serialized, right? If you have these two radically different sandwiches, they're going to end up making one sandwich and then the other. So it'll be slower than two employees for that. Okay, so now we get into the C++ part of this. How are we actually going to express this in C++? How are we doing on time? Not great. Okay, so I'm going to speed up. Where are my cards, by the way? Oh, you're here. Okay. Okay. Oh, that's right. We're doing, I got the hour. So we're just right at almost at the 30-minute mark. No, I'm doing great then. I got my times. I forgot we were starting at 15 after the hour. Okay, so what kind of code can be vectorized? Well, data parallel, that's the thing you should be thinking of. If it's data parallel, then it's maybe a good candidate for vectorization. A whole bunch of data items, same computation, more or less, on all of them. That's what you should be looking for. Now, I have a confession to make. I was at a talk yesterday about know your hardware, and the question was asked, why did the compiler produce faster code for this than for that? And the answer was because it can vectorize it, and I didn't get it right away. So that lets you know the limits of my, my expertise, because I'm used to thinking of, if I want to do this computation, how do I vectorize it? I'm not used to thinking of, this computation was vectorized, how did it get there? It was just kind of a backwards thinking. Anyway, so the kind of code that can be vectorized, data parallel, no unstructured control flow, like gotos, dependencies that are consistent with Wavefront, and no inter-iteration synchronization, except for some things that we know to be fast, but no like mutexes. So we're going to revisit that Wavefront thing I just mentioned, right, that we talked about before. And the computation on the left can be vectorized because we are sure that that first computation is going to occur with the purple arrow, okay, that first computation is going to occur before the thing it points to. So that matches the serial order of things. And we always aim, when designing parallel systems, whenever possible, we aim to have serial semantics, which means if you could execute this completely serially, if you execute this completely serially, you will get the same answer, or the same range of correct answers at least, as using whatever parallel system, whether it's vectorization or multicore or whatever. So we call that serial semantics. And serial semantics are preserved in the first case because that write to a sub I is guaranteed to occur before the read from a sub I minus 1 on the next iteration, which is the same value of the array. It's really clear how these two elements of A are the same element. Okay, so they are talking to the same element, but they are sequenced. SIMD guarantees the sequence. Vectorization in general guarantees that sequence. Parallelization does not. So we see that diagonal line of the wavefront. We can be sure that at some point it's going to have crossed the first computation and will not have crossed the second. Okay, the other dependency here, when we reverse the statements, cannot be true. Is not dependable. It's indeterminate, in fact. We do not know at the time that we are reading a sub I minus 1 over here whether or not the previous computation in the previous iteration has completed. And it's, first of all, it's bad because it breaks the serial equivalence, but it's even worse because it's actually indeterminate. You don't know. And you'll get different values over the course of the loop depending on whether these computations crossed a chunk boundary or whether they were part of the same chunk. You'll get different answers. Okay, so almost certainly not the correct answer. Okay, so that's another view of these wavefront dependencies. It takes a little while to get the hang of what is and is not a wavefront dependency. Fortunately, loops tend to have fairly straightforward wavefront dependencies. So the error rate is not all that bad, but it certainly does happen where people say, oh yeah, this is vector, and it's really not. So when you're programming, so now we know what kind of loops can be vectorized. How do you get the vectorization from the compiler, operating system, and whatnot? Well, the operating system is really not involved. Vectorization is inside the CPU. It's at the user space level. It's done by the compiler. So the compiler, AutoVectorization, is the oldest and still the most common way to get vectorization. You rely on the compiler to do it all for you. So the compiler has to recognize the pattern. It has to decide whether this is worth vectorizing. So it does this cost-benefit analysis based on how much code it needs to generate, how much control divergence there is, and things like that, which I'll get to in a minute, and does this computation and decides whether to vectorize it or not. It has to prove, and I'm not sure which order the compiler does it in, whether it does the proving first or the cost analysis first, it has to prove that this is a valid vector computation. Now think about that term, prove, right? Anything that is suspect has to be thrown out. Anything that could impede vectorization has to assume that it will impede vectorization, and the compiler has to give up at that point. So it doesn't always succeed. Even when the loop, to a human observer or to the programmer who knows all of the inputs and outputs, can say, yes, this should be vectorizable, the compiler may fail to vectorize it. Now, we keep getting better at this. I'm from Intel, so I'm kind of obligated to say the Intel compiler is the best at this, at least for the Intel architecture. But there are some constructs that GCC will do better at for, where ICC might give up and say, no, I can't vectorize this, and GCC will actually see through it, and vice versa. All right, so you're very, very much at the mercy of the compiler's ability to prove that this is vectorizable. So what hurts AutoVectorization? Well, a lot of the things that hurt any kind of vectorization, but specifically for AutoVectorization, any kind of possible aliasing that could violate your wavefront rules. So if you have this computation on X and Y, which are our arrays going into the computation, and X and Y might overlap, well, certain overlaps are okay. Other overlaps would be a violation because you would end up with, say, if Y came before X, I don't remember, yeah. I didn't do the analysis, but there's a type of overlap. It's kind of like that mem-move versus mem-copy problem, where there's certain overlaps that mem-copy can handle and others that it can't. If the compiler doesn't know, it has to assume that you have a dangerous overlap and it won't vectorize. Unknown alignment. I'm going to mention alignment later, but it may not be profitable to vectorize if we don't know whether the arrays are aligned on these vector boundaries. Opaque function calls. If the compiler cannot see through to the function it's calling, it can't vectorize that function. In general, there are notations that will allow it to do vectorization across opaque function calls. But in general, if it can't see that function, then it can't vectorize. And if you have too many opaque function calls within the body of your loop, it's not profitable to vectorize. If you have one, it may still be profitable. You vectorize everything up to the function call, then you call the same function 4 or 8 or 16 times, and then you keep going back to vectors. So it's not a death knell, but too many opaque function calls, and the AutoVectorizer gives up. A lot of control flow divergence, especially like break and continue and go to. Gathers and scatters. Again, all of these things impede they make a lot of these things, like the aliasing actually could cause the compiler to give up, whereas most of the others cause the cost function to overflow so it says, no, this is too expensive to vectorize, so I'm not going to bother. So to maximize AutoVectorization, you want to minimize those things from the previous slide. In order to have the compiler have the best chance of recognizing this as the kind of loop it might even try to vectorize, you want to make your control constructs as transparent and boiler like a cookie cutter as possible. So this is a very straightforward for loop that just counts from 0 to n-1. Okay, am I live? Yes, good. Okay, so this the for loop, yeah, straightforward. Any compiler should be able to recognize that as a straight counting loop, knows how many iterations there are in advance, can do all sorts of computations on it. The C restrict keyword, this is from C, and it was added in, I believe, C99. It is not part of C++, but a lot of compilers support it to some degree or another. And it basically says X and Y are independent arrays. They don't overlap. So that if you can use it with your compiler, or it might be spelled a little different, it might be _R restrict because it's not standard for C++. But if you know the compiler or set of compilers that you are using support it, you can use restrict. Assume align, same thing. This is not standard, but a number of compilers support this or something like it. You might need to use a macro so that depending on your compiler, it's a slightly different spelling. And says, let's assume that X is aligned on 16 bytes, for example, which is good for SSE4. And now the compiler has a lot of information that it says, oh, I can vectorize that. Not only can I vectorize it, I can vectorize it very profitably. The alignment, for example, gives it a lot of information on profitability. And the restrict gives it a lot of information on whether it's legal to vectorize. By the way, the compiler, even without the restrict, the compiler could still theoretically vectorize this, but it would have to generate two versions of the loop, a vectorized and a non-vectorized version, then look at x and y and understand the relationship with n to say, yes, they don't overlap, I can use the vectorized version. And again, the profitability is a big question there. Yeah, it would be a runtime decision as to whether to use the vector version or not. Now, that may sound bad, but remember that modern processors also have branch prediction. And so if it's always valid to use the vector version, after the first time it's made that decision, it'll be lickety split. It'll just go into the vector version every time unless and until that computation shows different. So it's not necessarily impossible to use profitably. And the last thing I mentioned is inlining, so that you can see, you can vectorize function calls. The important thing to remember about anything having to do with AutoVectorization is in order to get the AutoVectorizer to do what you want, it's a black art. And it's compiler specific, and it's CPU specific, and it's day of the week specific. I mean, it's microarchitecture specific. It is profitable from a human standpoint to do this if you are writing an application for a very specific machine or set of related similar machines, and you really, really want to squeeze the performance out of the machine, and you don't want to go to assembly language. And that happens often enough, believe it or not, that people actually do this. If you're working with particle accelerators and you've got a specific supercomputer that's made up a whole bunch of SIMD cores, you may spend quite a bit of time with the compiler getting compiler reports saying this loop got vectorized, this one didn't, and this is why, and so on. So when it comes to vectorization quality from compilers, there's not only the issue of how well does it auto-vectorize, but how good are the reports to help you figure out why it didn't auto-vectorize. All right, but AutoVectorization is really what we want to leave behind if we can, and instead move to something more explicit. And the best way in today's world to do that is with OpenMP. Now, one thing to know is some people really have an aversion to OpenMP, and there's a couple of reasons for that. Some people just don't like pragmas. For those people, I say get over yourself. And some people they don't like the overhead that OpenMP puts into parallel computations, which can be significant and doesn't scale well when you have nested parallelism. A lot of those things have been corrected in OpenMP recently, but the most important thing is that the SIMD part of OpenMP is affected by none of that, except for the pragmas. I mean, it is still affected by, it's still pragma syntax, but any overhead that the parallel threading part of what OpenMP puts in there, and there are some weird parts of that model where it exposes the threads and things like that that are not very pure, none of that affects the SIMD portion. So you can go ahead and use OpenMP SIMD and not drag in a runtime library that you don't want and things like that. So OpenMP SIMD is, it's a guarantee to the compiler that I have thought this through and that I don't have any aliasing that would violate the dependency rules, and I have a standard form countable loop. If you don't, it's actually a syntax error. And that I don't have any loop carry dependencies that would violate our rules, except for reductions and inductions, which have to be explicitly called out, and I'll get to those in a minute. The other way that I'm going to mention right now is a proposal that's in front of the standards committee for getting basically that same functionality into C++ next. It's not getting into C++ 17, and part of why we didn't get into C++ 17 is because actually writing down the wavefront computation in something that approaches standard ease was really hard. And when I look at it now, it's like it didn't look so hard when you read the actual text now, but boy, we went through iterations that were horrible. So what this is using a syntax that looks like a function call, because it is a function call. It's a function template for loop, which works kind of like the parallel STL. I don't know how many people here have been exposed to at least the basics of how the parallel STL looks. Okay, about half of you. I'll quickly mention for everybody else, it's a set of algorithms that most of which are also present in the standard serial STL, but they have one extra parameter at the front saying parallelize this using either normal parallelization or using parallelization with vectorization. And we don't have one for vectorization only right now. It's in the proposal phase. And the reason we don't have that was because of what I just said about being really hard to specify the rules. When you combine parallelization and vectorization, you get the intersection of the guarantees, which means I don't have to make a guarantee that I can't describe. Okay, I know that may sound funny, but it's still a useful concept. So the vectorization without that wavefront guarantee, that's just called unsequenced execution. So that's the unsequenced policy, whereas we're proposing a vector policy, and we hope to get that into C++ next. So what it looks like here is a for loop is an algorithm. It's a function call. The first parameter says, do this function call using vectorization. I, as the caller, as the programmer, am guaranteeing to you that I've met all the rules for something being vectorizable, same as the OpenMP SIMD. And we're going to iterate from 0 to n, well, 0 to n minus 1, and pass the argument, that value in as an argument to our lambda here. And then the computation is the same computation we saw before. Okay, that's the Saxby computation. Right, so it's just a different spelling of like the OpenMP, yeah.
Is there an intention to have a core extension to make it more for loop-like?
Yeah, so the question is, isn't it kind of ugly to express something that is like a for loop, but using this library syntax? This was a big argument. It may come around again, but the direction that the committee chose is to make new control construct-like things work like these algorithms. There are a few of us who are interested in future language extensions to make this prettier. But that's the status quo. And it doesn't look quite as bad if I didn't squeeze it into this narrow slide either, but it's still, yeah, it's still not as nice looking as a for loop. Okay, you know, you remember my rhetorical, this is, you know, assume a for SIMD. This was actually proposed at one point. And it didn't pass because, largely because some of the parallelism stuff is not, it was not thought of as being stable enough for standardizing a new control structure that was part of the language in C++ 17. It was like, there was a thought that there are too many knobs that you might want to tweak and no way to express them once you have settled on your keywords and your syntax. So we might stick with library for a while until we have all those knobs figured out, and then we say, well, but 90% of the cases don't need all those knobs, or they need just this set of knobs, and then maybe we'll come up with a language syntax. Reduction and induction variables. So a reduction is when you have doing a parallel computation and you are accumulating the result into a single value. This is a very common pattern in any kind of parallel computation or serial computation for that matter. But when you're doing something in parallel, how do you do this? The wrong way to do it, by the way, is with an atomic. This is the way people reach for an OpenMP all the time, and it is the wrong way to do it. Atomics are slow across threads. They kind of serialize a chunk of your code. So the right way to do it is to use a construct that the parallel system, in this case OpenMP on the left, or the proposal on the right, gives you to do reductions. Because what was actually happening under the covers, there's no atomics actually happening here. Instead, the reduction, which is this first sum here, where we're adding things into an accumulator, and there's different kinds of reductions besides adding, like you could OR them together or multiply them or whatever, is that it's telling the system that you are you are doing a reduction. And what it does is it sums that, suppose we have 4 lanes. It's going to sum things 4 lanes at a time, keep those 4 partial results, go on, do the next chunk, keep adding into the same 4 partial results, and onward. And at the very end, it sums those 4 partial results into one final result. No atomic operations, no barriers, no nothing like that. Please hold your questions because I'm running out of time. On the right is the, I'm not even going to go into too much detail, but this is sort of what the library solution is for this. See how we're adding clauses? And this is back to that syntax question. So long as we have not yet seen the last clause to add, doing it in a language extension, it gives people it makes people nervous, right? But for library stuff, it's really easy. You just add another overload or another interpretation of your periodic template arguments. So we added this reduction clause, reduction plus, a sum, and induction. So the induction is the other thing. And induction is this thing that happens linearly where you have a variable that it tracks the loop control variable, but it might go in increments of 2 when the loop control variable is going in increments of 1 or something like that, as we have here. And again, the iteration I sets a value, iteration I plus 1 needs to have seen the change from the previous iteration. How do you do that in parallel? Well, because you know it's linear, you can pre-compute it for the entire 4 lanes of your SIMD computation. And then you jump. Instead of incrementing by 2, you increment by 8 for the next chunk. And then pre-compute, add plus 2, plus 4, plus 6 for the next lanes. The last thing I'm going to mention is the way of getting this into your C++ code is with these class libraries. So these are libraries that mimic the SIMD registers. They're kind of like a CPU agnostic or a portable way of expressing these SIMD registers. So you don't have to use compiler intrinsics that are specific to a CPU, and your computations look a little prettier. They try and give you that really low-level access to the SIMD without tying you to an architecture, to a microarchitecture. So this is what boost SIMD. This is the SAXP computation one more time using boost SIMD. We create a pack. A pack means a packed set, effectively a SIMD register's worth of floats. Okay, and there's ways to deal with multiple architectures like I don't have time to go into. And you say, well, how long is that? And what we're going to do is go through our loop and increment not by 1, but by an entire SIMD register's worth. We're going to suck up a SIMD register here of data from X and 1 from Y, and then do our multiplication and addition here. Scalar by vector multiplication means multiply every value in the vector by that same scalar. And we're going to store the result in Y plus 1. And we're using this aligned store thing, which says, use the most efficient way to store it, which is assume that these things are aligned. Okay, there's a lot to be said. Now, there's a proposal, I mentioned it here, P0214. It's kind of similar to Boost SIMD, has some important differences, and we did a lot of work on it, and it's progressing forward through the standardization process. So we could use, and one of the things we're going to try and do is integrate it with the parallel STL and get the benefits of both, so you can mix the 2 approaches. Pros and cons of the SIMD libraries. Well, eventually they might be integrated with the parallel STL. Cons, you can have ABI problems if you're using different architectures. There's work we have done with the proposal so that at least you're likely to get, likely but not guaranteed to get a link time error if you do this mixing. One of the big advantages, very explicit, you have total control. That's also a disadvantage. Too much control, too much rope to hang yourself with, too much work to get the job done. So I'm going to very quickly skip through this because I'm really running out of time. The ways to get the most out of most performance. I mentioned this alignment and size before, so I won't go too much into it. Suffice to say, you want your things aligned. You want, if possible, to have exactly the same number. You want to have a multiple of vector width on your loops. Sometimes that's not practical. You have exactly this much data. Okay, so you'll have to pay the cost for a remainder loop. That's not the worst thing in the world. Okay, the last thing here in the yellow, If possible, let your compiler know that you have created everything aligned and so forth, and then the compiler can optimize accordingly. But like I mentioned, with branch prediction, not always such a big problem. Data layout. This is a big topic, so I'm going to go mention it very quickly. Ideally, you want all of the elements of the same type to be contiguous. Unfortunately, when you have an array of structures, they're not contiguous. So we've got double int, double int, double int in this array over here. So if we just kind of turn that inside out, and instead of an array of structures, we make it a structure of arrays, now we have all the doubles together and all of the ints together. And that makes our loads and stores much more efficient. Okay, so this is called AOS, SOA. There's a new product, part of the Intel 17.0 compiler that is called SIMD Data Layout Template, SDLT, that will automatically do much of these transforms for you. It's very cool. You can combine thread and vector parallelism. The most efficient way to do it is to make your outer loops parallel and your inner loops vector. You can't do it the other way around because you can't really do parallel computations inside of a single SIMD register. So that's a really good rule of thumb. That's about all I'll have time to say about that. So I have a few minutes for questions, and then I've got a conclusion slides. Questions? Is there a microphone? No. So just say your question, and I will repeat. Over here. Vector, yes, so the question is, for the plain STL algorithms, will the compiler vectorize them? Often, yes. If it's the kind of thing that meets all the requirements and the compiler can understand the dependencies and so on, yes. So a straight like for each, quite possibly, the compiler will auto-vectorize.
So if I'm deploying to multiple microarchitectures, is there anything that will help me get the best performance on the computer that's actually running the code?
So the question is, when you have multiple microarchitectures, is there any way to get the best performance on the computer that's actually running the code? Yeah, it depends on the compiler to some degree, but there are flags. And sometimes you can say, generate just for, say, AVX512, which is the best that we got, right? In which case you can't run the code on anything else. Or generate for this set of microarchitectures that might not include the oldest ones. And then the compiler will actually generate runtime ifs. And again, branch prediction, they don't cost very much, those runtime ifs. They cost code bloat, but they don't cost much in runtime. So yeah. Any more? One more.
Instead of the creative STD for loop thing, wouldn't it have been easier to just use for each, which is there?
So the question is, wouldn't for each have done the job of this separate for loop? Not exactly, but we have considered it. The big thing that the for loop provides is that it's index-based rather than iterator-based. In order to go from iterator to index is this ugly and somewhat silly backwards computation where you have to have a generator that generates a list of integers and have iterators that iterates over the generator. And we actually don't have the right kinds of iterator types yet to do that correctly. So that's one problem. And the other thing is that that wavefront dependency is only really useful when you've got, well, it's not the only way it's useful, but it's often most useful when you've got multiple arrays. When you're looking forward or backwards, which from an iterator is kind of an ugly thing to do. Oh, well, let me look at the +1 element and then -1 element. Whereas if you're using indexing, it's very clear what's going on.
So the second part was that, as far as I'm aware, there was a proposal for a thing called a bounds iterator, which provided precisely indices into a domain as opposed to, I don't know if that went.
Right, so there is a proposal for the iterators, and like I said, we don't have the correct iterator categories yet for that proposal to go forward, but they're coming, we hope. The other thing about the for loop is that it has all these extra clauses like inductions and reductions that for each doesn't have, but we could add them to for each. So that would be the other way to do it. So, yes?
If you change your code to try and have the compiler auto-vectorize it, is there a way to tell whether that's actually happening?
The question is, if you tinker with your code to try and get it to auto-vectorize, is there any way to find out whether it actually did? Yeah, aside from reading the assembly language, most compilers, and certainly the Intel compiler, will produce a report for you about what got vectorized and what didn't. And often, why it didn't get vectorized. It'll say there's a loop carried dependency on this variable or something like that. So I'll stay a little bit longer. We have a little bit of time between this and the next session. I can stay longer for other questions, but let's wrap this up. So use those SIMD units. It is a little bit of a black art that we're still catching up with standardization and so on, but for data parallel code, you can get these big speed ups because that hardware is in there and it's very energy efficient, and you don't want to leave that performance on the floor. You don't get the scheduling overhead of other kinds of parallelism, so it works better for small computations. But you have limits, right? You have to minimize the control flow dependencies, minimal control flow dependencies, divergence, control flow divergence, what I should have said. But you can make a great sandwich using SIMD. So thank you very much.